So today, we're going to talk about the quantum chemistry, and so we're going to talk about the relationship between quantum chemistry and spectroscopy. And so, during the practice session, so some of you may have already done already, but by using quantum chemical calculation programs, we can predict the we can predict the optimal optical properties. So spectrums of molecules, using quantum chemical calculation programs. But before that, so we have to understand so what is the spectrum and what are the peaks and how can we interpret the experimental data and theoretical calculations. So first, so light. So light is electromagnetic wave. That is one of the most fundamental things that Maxwell proved about 100 years ago. So light, as you have already studied, light consists of electric field and magnetic field, and they are orthogonal to each other. So the electromagnetic field can be thought as so here so you can think that this red wave is an electric wave, and you can think that this blue wave is magnetic wave. So the electric wave and magnetic wave means that so light has the property of can interact with charges or magnets. So when light comes hit an object, and so light contains electromagnetic wave. So if you think about electric wave, so the electric wave oscillates like this, and so the electric wave oscillation of electric wave means that so it can affect it can give some effects on charging particles, right? So when you think about so we can think about a molecule like this. So when we have an example molecule like HCl, and most of you already know that so the Cl likes electrons, so it is slightly negative charged, and this H has slightly positive charge. So you can think that most of two atom molecules like this. So if they two are not identical, then so one may like electrons more and one doesn't like electrons, then this one will be negatively charged and this one will be positively charged. Then if electromagnetic wave hits this molecule, then because this electromagnetic wave is oscillating, so if positive charge comes to here, then so it will be attracted to here, and this one will be attracted to this direction. But as time goes and electromagnetic wave oscillates, and if this part becomes negatively charged and if this part becomes positively charged, and they both will be repelled from the both ends, and so this will be shortened, and here this will be lengthened, right? So since light contains electric field, so molecule can interact with light. So if molecule has dipole, if molecule has a dipole moment, then it can interact with light. So we have to talk about dipole moments, right? So actually, so you have heard about dipole moments since you were since your first year. So what is dipole? So the dipole means di means two, right? And pole means end, right? So dipole means, there are 2 points, 2 ends. So the 2 ends means, so one is positively charged and one is negatively charged, and they are connected by a certain length r. So in this case, so this kind of object is called dipole. So why do we care about dipole? Because dipole is everywhere in nature, and for most of molecules have dipoles. For example, for a water molecule, so this oxygen has negative charge, and these hydrogen atoms have positive charges. So they have two dipole moments. One is like this, and the other dipole is like this. And the direction of dipole is starting from the positive charge and going to the negative charge. So they can be represented as a vector, right? Starting from the positive charge and going to the negative charge. And the magnitude of this dipole moment, is considered as Q dot R. So Q is, if this one is has charge of plus Q, and if this one has a charge of minus Q, then the magnitude of this dipole, so the magnitude of dipole can be written like this. So they are written here. So yeah, I inserted some Koreans because so these are a little bit, I think a little more difficult than previous classes. So they have some physical concepts. So to help you understand that. And there are two types of dipole moments. And so one type is static dipole moment. So the static dipole moment is that, so they are induced. They arise due to the 3D structure of a molecule. For example, for a water molecule, so it has a bent structure, right? So it is bent. So water molecule, the angle of water molecule here is 104.5 degrees, as you know. So this one is bent, right? Bent, right? So this one is bent. So it has dipole here and dipole here. And if you sum up these two dipoles, then their sum will be like this. So you need the vector addition, right? But in case of CO2, this CO2 also has dipoles because this is positively charged and these oxygens are electrophiles, and so they are negatively charged, right? So they have two dipole moments, but their dipole moments the direction of dipole moments are exactly opposite, right? So their magnitudes are same, but the directions are the opposite. So their sum, the sum of, there's just only two. So this vector plus this vector results in 0. So some molecules, especially asymmetric molecules tend to be polar molecules, right? So I think you already know about this. And in addition to that, that is one of the basic principles of classifying which ones are polar molecules and which ones are non-polar molecules, right? So polar means this and right? And in addition to that, there are another type of dipole moment called induced dynamic dipole moment. So the induced dynamic dipole moment is that, so when molecules were just staying there, and even for polar molecules, even for non-polar molecules, sometimes in case of CO2, so this one has this kind of electron cloud, right? But sometimes, temporarily, so this part can be negatively charged and this can be positively charged. Then the neighboring molecule, the partial charge of neighboring molecule is induced by this one. So this one is induced, right? So this one affects this molecule, and here the negative charge is induced. And if this part becomes negatively charged, then the other part becomes positively charged. So this is called induced dynamic dipole moment. And so even for non-polar molecules, they can have very weak dipole moments. So in nature, there are two types of dipole moments. And these kind of dipole moments are actually the reason of interaction between molecules and light. So because of these dipoles, so molecules can observe or emit light. And so first, so we're going to talk about, vibrational spectroscopy, so IR spectroscopy. So I think most of you have already understood, studied about the vibration of molecules, right? So so when molecule vibrates, the frequency of harmonic oscillator. So the frequency of harmonic oscillator is written like this, and so here the mu is frequency, and here this is mu, and this is mu, and this mu is an induced. This is a reduced mass, and this is force constant. So So when an object with a mass of m1 and m2 is oscillating and vibrating, so we can calculate the frequency of this oscillator by using this equation, right? So here this is reduced mass. So mu is m1 plus m2 over m1, m2, and k is a force constant of this spring. So the force constant means if this k is large, it means that this spring is very stiff, and if k is small, then it means that this spring is weak. So if you look at this equation, that it means that so mu increases as m1 and m2 increases. So this means that the heavy molecules vibrate slowly, and k becomes large. So if spring is large, then they oscillate faster. So based on the property, based on the mass and the nature of their chemical bond, so each molecule vibrates at its own with their own characteristic vibrational frequency. So these are the vibrational frequencies, specific vibrational frequencies of each molecule, right? So by observing them, by measuring them, so we can see that, if some molecule observes light with a frequency of 4,400, then we can think that, that molecule must be hydrogen molecule. Or so by measuring these, so we can detect, so we know, so which molecules are there, right? So that is one of the most fundamental goals of spectroscopy, right? But in spectroscopy, so there is a very important rule called selection rule. So the selection rule means not all transitions are observed with spectroscopy. So which means that so molecules can vibrate in several ways, and also so they have multiple energy levels, right? So they have multiple energy levels, but so not all transitions, like so from ground state to, so let's say that this is the first excited state and this is the second excited state. So we can think about many different transitions, but not all transitions are observed by spectroscopy. And so that is generally called selection rule. And there are many selection rules in physical chemistry, but in other words, so only physically allowed energy transitions are observed with spectroscopy. And in terms of quantum chemistry, in terms of quantum mechanics, so we can say a transition between quantum states N and M can be expressed with this integral. So it only occurs when the following. So this is called transition dipole moment integral, and this transition dipole moment integral is when this is not zero, so they can observe light when a molecule changes its state from N state to M state. So we're not going to solve this integral, so this is too hard. So but so physically, so you can just you can just understand that so not all transitions are observed because of some quantum mechanical reasons. So we're going to, so not solving equations, we'll just, describe so which motions and which motions are coupled with, which kind of, spectroscopies. So first, so we're going to focus on vibrational motions of molecules. So for example, for the example of CO2, so CO2 consists of 3 atoms, and it can vibrate in 3 different ways. So the first one is symmetric stretch. It can vibrate like this, and the next mode, the asymmetric stretch is vibration occurs like this, and so one becomes shortens, but the other bond becomes lengthened. And the last mode is called bending motion. So the bending motion means that so you can bend like this. Right? So CO2 can oscillate in 3 modes, and these kind of vibrational motions can observe. Maybe I should have put one more slide. So the vibrational motions observes what? IR spectrums. Oh, I should have talked about it first. So the vibrational motions observe infrared light, right? And what other motions? Molecules also can rotate, and rotational motions observe which light? Microwave. They observe microwave, right? And what is it? An electronic structure. Electrons observe visible or UV lights. So we'll talk about this later, but so now we mostly focus on this one. So when we detect, when we want to detect, measure vibrational motions of molecules, so we use, infrared spectrum, infrared laser. So if you take the IR spectrum of CO2, then you get a plot like this. So there's a small peak, but I don't know what it is, so we'll forget about this. And so if you see this, this peak corresponds to the vibrational motion of this one. And this peak corresponds to the vibrational motion of this one, bending motion. And see, but as we mentioned, so CO2 has 3 vibrational modes, but this mode is not observed in IR spectrum because, so we're not going to solve this, but we can prove that IR spectrums are observed only when dipole moment changes. Only when dipole moment change occurs. So if the vibrational motion of a molecule changes its dipole moment, then that motion can observe IR spectrum, IR light. But if the dipole moment doesn't change by vibration, then that motion does not observe light. So it means that so for symmetric stretch, in case of symmetric stretch, so because 2 dipole moments are stretched at the same time, identically, so with identical magnitude. So this motion cannot observe IR spectrum, but this mode and this mode can observe IR light. So we can see the peaks of these 2 modes, but we cannot see the vibrational motion of this one. So in this case, so we say that so these 2 motions are IR active, but we say that this motion is IR inactive. And in case of H2O, so H2O also can vibrate into 3 different ways. So the first is symmetric stretch like this, and bending motion and asymmetric stretch. But in case of H2O, if H2O vibrates like this, does dipole moment change? Actually, the answer is yes, because although this is symmetrical motion, but what is it? So the dipole moment goes to here, right? And the sum of the dipole moment is not zero like this. And as I mentioned, the magnitude of dipole moment is Q dot R, right? So as this one stretches, if this one stretches like this, then the length of R, so the distance becomes large. So R increases, right? So the magnitude of vector increases. So the sum of these two vectors, the magnitude also increases. So although this motion is symmetric, but this mode is IR active. And also in this case, what about this? So the bending motion, in case of this bending motion, so the dipole moments were like this, but if this one bends like this, then dipole moments becomes like this. So if we add these two, and it is like this, but when this one is bent, when this one is more bent, then the sum of these two vectors will increase. So this one also changes the net dipole moment, and also this one also changes the net dipole moment. So in case of H2O, all these three vibrational modes are all IR active. So there is a one peak and second peak and third peak. So in this plot, so this is a transmittance. This red line shows the observance. So when this red line is 1, and it just goes through a sample. But if this red line becomes 0, then all lights were observed by the sample. So all these three molecules are IR active. So in short, so we can use infrared light to see how molecules vibrate. And by using that, so we can detect which molecules are there. But not all vibrational modes are active. Right? So in addition to infrared spectroscopy, so there is also another very famous spectroscopy called Raman spectroscopy. And Raman spectroscopy is the major research subject of Professor Zhang's group. And so if you want to know more details, so you can ask her. But so I'll just give you a very brief explanation of what Raman spectroscopy detects. So the Raman spectroscopy is called because the Raman scattering was discovered by this Indian physicist. So his name is I don't know. So anyway, so he's a very famous Indian physicist, and so he received his Nobel Prize in 1930, and so this is the first spectroscope. This is the tool that he first observed the Raman scattering. So he observed this in 1928. Which looks very old, right? So what is Raman scattering? So the Raman scattering means that so one basic visible example is shown here. So from here we generated the green laser. So the green laser hits this lens. Then we can see that the green light is reflected from this lens, right? So here the green laser is coming from here, and it hits this lens, and it is reflected, and we see green light here. But as this one transmits this lens, because so this lens is placed a little distorted way. So this one reflects, but some light goes through this lens, and it hits this wall. But if you see that transmitted or scattered light, but the color is red, right? The color is red, so not green. So which means that the wavelength is changing. And so this kind of phenomena is called Raman scattering. So I'll give you more details about Raman scattering. So let's say that these are the energy levels of molecules. So these are the energy levels of molecules. So this is the ground state, and these are excited states, right? So if we give some light, if we give some energy to the molecule, then it will be excited, but after some time it will go back to its ground state. So in this step, it observes energy. But when it changes from excited state, to ground state, then its energy level becomes lower, and it should emit. It should emit energy, right, by the form of light. So it means that if we hit a molecule with laser, then first it observes energy, but after some time, it emits the same energy, because most of the cases energies are conserved. But sometimes, so if we hit the molecule, then it observes energy, but it comes down to not to the ground state. It comes down to this state. Then so it emits so less energy than it observed, right? So it emits less energy. So the scattered light has less energy than the incident light. So this one is incident light, and so first I should define some terms. So when we have a molecule like this, so this is the famous phenomenon called scattering. So we can hit a molecule with light. So then this one is called incident light. This one is called incident light. But as this one hits, some lights are scattered. So if you play pool, so you can easily imagine that if you hit a ball with a pool, then so it just scatters, right? So you can think as this is a scattering. This is scattering, and so some lights. So if we give an energy of 100, then most of lights emits the energy of 100. But sometimes a molecule emits only about 90 of energy, or in some cases, it emits more energy than the incident light. So those are called Raman scattering. So this kind of scattering is called Rayleigh scattering. So this is not something special, but but Raman scatterings are more special because it changes its energy level, and these are much weak. So it is a little harder to detect. So if we hit a sample with laser, then it scatters. So light scatters. So light scatters, and some lights are called Rayleigh scattering, but some scatterings are called Raman scattering. So the Rayleigh scattering has the same energy with the incident light, but spoke and anti-spoke Raman scattering has more or less energy than incident light, right? So you can think about this diagram. So actually, as observing this light is usually what IR spectrum does. But measuring these Raman scattering in Raman spectroscopy, we observe this kind of Raman scattering. Then what does Raman spectroscopy observe? Then in IR spectrum, I told you that IR spectrum observes the vibration of molecule. Then what does Raman spectroscopy observe? So the Raman spectroscopy actually observes the change of polarizability. So the polarizability is, I should have put some green here. So the polarizability is polarized. Polarized means, right, ability. You know what this means, right? So the polarizability is translated like this. So if we write down this, a little more formally, then so polarizability is written like this. So here, so P or D, this one is dipole moment, and here the alpha is polarizability, and E is electric field. So if we put some molecule, so let's say that so we have a neutral and non-polar molecule, and it has no dipole, right? But if we put this in an electric field, so if we give plus charges here and if we give minus charges here, then what kind of changes will happen? So the electrons will be withdrawn to this way, right? Because electrons are negative. So the electrons will be drawn, so the whole shape, the shape of electron cloud will be distorted, and electrons will be here, and this part will be positively charged, right? So this is natural, right? So so by doing this, then dipole is induced. So polarizability means that when we give certain electric field, then how much dipole is induced by this electric field. So it means that so if we give some electric field, then so how much electrons, how much the shape of electron clouds are distorted. So if this one is very, how should I say that, sensitive, then it will have very large polarizability. But if electron cloud doesn't change, doesn't move that much, then it has low polarizability. So the Raman scattering, actually, so people, discovered that Raman spectroscopy observes this kind of the change of polarizability. So this is a little harder to visualize, but so we'll see some examples of CO2 again. So for CO2, as I mentioned, so it has 3 modes, right? It has 3 vibrational modes. So one is symmetric stretching, and one is asymmetric stretching, and one is bending, right? Bending. So so if we think about CO2, then so it has electron density like this, right? But as this one vibrates, so let's imagine that so this one is vibrating and oxygens are stretched like that, then electrons will be dispersed more, right? So if we exaggerate it a little bit, so the electron clouds, at first electron clouds will be like this, but as this one stretches, as this one vibrates, then electron clouds will change, right? So from here to here, so as this one, what is it? The length of arm shortens, then the electrons will be centered around here, right? So the whole shape of electron clouds changes a lot, based on this vibration. But for this vibration, so since so one oxygen stretches, but one oxygen contracts, so so the whole electron density around here doesn't change a lot. So the electron density doesn't change a lot, and also in this case, so the whole shape of electron density doesn't change that much, so compared to this one. So if we observe Raman spectrum of CO2, then so we can only observe the Raman spectrum of this symmetric vibrational mode, but we cannot see the peaks around here because these doesn't change the shape of electron clouds that much. So so this is the exact opposite of IR spectrum, right? So in IR spectrum, this one was not observed, but in Raman spectrum, so this one is observed, but these are not observed. So these are Raman inactive, and this one is Raman active. But in terms of IR spectrum, so this one is IR inactive, these ones are IR active. Right? So from this example, so you can see that infrared spectrum, IR spectrum, and Raman spectrums are complementary. So complementary means so kind of help each other. So some mode can be active for both, but some mode can be observed with IR, but some mode can only observe with Raman, and some mode cannot be observed with both. So they are kind of complementary. So so in case of CO2, CO2 is a very simple, easy example, but in reality, so we generally want to know, what kind of molecules are in sample, and generally, so we want to analyze complex, larger, organic molecules, right? So organic molecules generally, large organic molecules have many peaks, and so in many cases, so IR spectrums are not enough, to detect, certain molecules. So we have to, in many cases, we use, both. And also, so Raman spectroscopy, and another reason why Raman spectroscopy is, very popular is that, it has certain advantage. So one of the main advantage of Raman scattering is that, so it can be applied to molecules in solution. So the reason is that, so if we, hit, IL spectrum to a solution, then, most of the IL spectrums, IL lights are observed by water. So, so if you think about the solution phase, so there are solutes, but most of them are water, right? So if we hit IL light, then this IL light can be observed not only with not only by this solute, so it can be also observed by water molecules. So the water molecules actually so prevents, so it interferes. So the IL spectroscopy cannot be applied to solution-based samples. But Raman scattering, so it doesn't have that kind of problem. So if you want to, analyze some very large molecule or the protein, sample in water, then so you can use them. So Raman scatterings are commonly used to analyze protein samples in water. So Raman scattering has some advantages. And this kind of spectrum, these kind of patterns actually can be calculated using quantum chemistry packages, quantum chemistry programs. So during the practice session, so especially so class B will practice how to calculate so IL spectrum and Raman spectrum using Gaussian program. And also so we're going to visualize so the molecular orbitals. So the molecular orbitals are, so we're going to calculate molecular orbital and visualize these. And so as you have already studied, so if multiple atoms are connected together and if they form a single molecule, then their energy levels are divided and they form certain form of orbitals, molecular orbitals. For example, so these are the molecular orbitals of water molecule. So here it means that the lowest energy electrons, so the lowest energy electrons are placed here. So the lowest energy electrons are captured around and exist around this oxygen nucleus. And if this one is filled, because of Pauli's exclusion principle, there are only 2 electrons are allowed in this orbital, right? So after this is filled, and the next electrons will fill this orbital. And if 2 are placed here, and additional, higher energy orbitals will be filled with electrons. So we're going to see, these, using the Gaussian program. And also, this is the example of molecular orbital of benzene. And so we're going to calculate this, and we'll talk about the physical meaning of these, a little more detail on Friday. And in molecular orbital, and one of the most fundamental and one of the most important concepts are HOMO and LUMOs, right? So the HOMO means highest occupied molecular orbital, and lowest LUMO means lowest unoccupied molecular orbital. And why do we care about HOMO and LUMO so much? Because if electrons are filled like this, and HOMO-LUMO gap, energy difference between HOMO and LUMO orbitals corresponds to the smallest, lowest energy gap, lowest energy that an electron can observe, right? I mean, so think about it. I mean, so if electron excites to this state, and if this one goes to this, it can go to this. But the smallest jump, but the smallest energy absorption, the minimum energy that it can observe is this one, right? I mean, so it can. So that is the lowest energy. So usually, so if we give some energy to a molecule, to a ground state molecule, then the first change, the easiest and the first change that can happen to a molecule is the transition is from HOMO to LUMO, right? So this transition has the smallest energy, so it can happen most easily. So this is the most easiest transition. So that is the most common transition we observe in chemistry, right? So generally, for this kind of organic molecules, for typical size of organic molecules, most of the HOMO-LUMO transitions corresponds to the UV and visible range. So most of the HOMO-LUMO transitions actually observe visible lights, and because of that, so if some molecule has some color, certain color, then it means that its HOMO-LUMO transition observes visible light. So if you are interested in some light observing or light emitting molecules, then so all those changes happen between HOMO and LUMO orbitals. So that's why we care about HOMO and LUMO orbitals generally. Yeah, so we're going to also calculate the and see the shapes of HOMO and LUMO orbitals so using the Gaussian program. And by using the Gaussian program, actually, so without doing experiment, so we can predict how much energy it will be observed by molecule. So we can do that also using the quantum chemistry program. So we're gonna do that on Friday. So that's the end of the theory session, and so I'll give you some comments on the final term project. So as I mentioned.